University of Chinese Academy of Science. Okay, please.
Wait, sorry. Okay, thank you. Good morning, everyone. I'm Kai-Fei Peng from Chinese Academy of Sciences, and today I'm glad to present our work on large-scale network emulation. So network emulation is a crucial and widely used methodology for evaluating new network technologies. And compared to other methods such as the event-driven simulators or hardware testbeds, network emulation strikes a balance between realism and practicality by constructing virtual networks that resemble real-world environments. And recently, there are two main demands for network emulation. So the first demand is scalability, which is driven by the emergence of the large-scale networks we listed here, including the satellite networks, global BGP networks, and data center networks. So emulating these large-scale networks require network emulators to construct virtual networks that contains 10,000 nodes. And the second demand is efficiency. So modern network innovation experiments and optimization tends to explore thousands of design choices. And when using network emulation, it is needed to execute thousands times of experiments to fully explore this huge design space. But unfortunately, we find such multi-time emulation experiment can take very long time, which is bottlenecked by virtual network construction. And constructing a large-scale virtual network for one experiment can take hours. To accelerate these multi-time experiments, it is an urgent demand to construct the virtual networks very faster. And to do this, many prior works use multi-machine for network emulation, and this indeed helps, but has some limitation because of their cross-machine communication bottlenecks, like the cross-machine delay or bandwidth contention, limiting the effect of these multi-machine solutions. And on the other hand, we take a different path, and we aim at building large-scale virtual network within a single machine. We analyze the OS kernel level bottlenecks of current emulators and introduce our SplitNN, a new single machine architecture based on multi-VM splitting and multi-NetNS splitting. With our SplitNN, we can reduce construction time of these virtual networks by about 99% and can construct 10,000 node virtual networks within just several minutes. And now let's review some background. So constructing a virtual network in network emulation usually involves two stages. And at first, the virtual nodes, or we call the V nodes here in the figure, are created as containers. And then the virtual links, or we call the V-links here, are constructed by virtual devices like VF, Linux bridges, and VXLANs. And these virtual devices are created with Linux, usually created with Linux Netlink APIs. And the back-end virtual devices are also often put into your network namespace, which we call the backbone namespace, or the BBNS here. In the state-of-the-art emulators, all the V-links are carried in a single BBNS, usually which is the host namespace. We call this architecture the uni-BBNS architecture. And in addition, most current emulators are deployed on bare metal. And then we profiled this uni-BBNS approach on bare metal. We find that virtual network construction time increases superlinearly with the topology size. And over 99% of the CPU usage is spent in the kernel state during virtual link construction. And why? We found two limitations from the OS kernel. And first, Linux kernel forces virtual link construction to be serialized. Linux uses a global lock, which is the RTNL lock in the figure shown here, to synchronize the Netlink API calls that construct the virtual links. And this prohibits virtual link construction from parallel acceleration. The The second kernel limitation is the high overhead from the kernel notifier chain. And we found that each virtual link construction triggers two costly kernel notifier functions, which is the flush and walk here. The flush function traverses all the network namespaces in the system, and walk function scans all the virtual links in the backbone namespaces. And in large-scale emulation, this traversal needs to scan many elements because there are many virtual devices in the network, and therefore these become very costly. So to address these two kernel-level limitations, we propose our SplitNN architecture, which comprises two mechanisms, which is multi-virtual machine splitting and multi-network namespace splitting. So let's introduce the first mechanism, multi-VM splitting. So on a single machine, we set up multiple virtual machines. And for each emulation experiment, we partition the input topology into many sub-topologies. Each of the sub-topology is run as a sub-virtual network in a separate virtual machine. And this parallelizes virtual link construction on a physical machine with multiple kernel instances, because there are many locks now, compared to the bare metal where there are only one global lock. But there's a trade-off. More VMs reduce time, but increase memory usage. And in this paper, we use an empirical value of a VM number. Through experiments, we find that 4 VMs strikes a good balance in our environment. The second mechanism of SplitNN is multi-NetNN splitting, which distributes virtual links across multiple backbone namespaces. This greatly reduces virtual link count in each backbone namespace we mentioned before, and therefore it greatly reduces the device traversal overhead caused by the kernel notifier walk we mentioned before. But again, a trade-off problem comes when we decide that how many backbone namespaces to use in a VM. So as the backbone namespace number grows in a VM, the walk overhead decreases, but the flush overhead increases due to the increased network namespace number. We need to balance these benefits and overhead by finding an optimal backbone namespace count in each VM. To find this best number, we formalize an optimization problem here, where we model the total time cost of virtual network construction time as a function with regard to the x, y, z here, which corresponds to flush, walk, and other overhead for each virtual link construction. The solution can be derived as here. And finally, the values of the hyperparameters x, y in this formula need to be measured. And we propose a sampling and a regression workflow to measure them on a given platform and derive the XY values as shown here. But due to the time limitation, we do not expand it here. So now let's move on to the evaluation. Our experimental environments are shown here. And we evaluate our SplitNN with 3 typical topologies, namely the grid, fact-sheet, and real-world BGP-AS topologies. Each of them includes about 10,000 of nodes. First, we evaluate the multi-VM splitting independently. We can see that as the number of VM increases, the virtual network construction time cost drastically reduced, but the gain diminishes with over 4 VMs. And with 4 VMs, memory overhead is controlled, and the topologies can be constructed in around 10 minutes, but it still not reached the minute level goal we mentioned before. Then we evaluate the multi-NetNN splitting, which shows great performance, and it can help to reduce the topology construction time into also around 10 minutes, but also multiple backbone namespace consumes very low memory, which shows the great scalability of using the multi-net NS splitting. Finally, we combine the multi-VM splitting and multi-net NS splitting together, and we find that with 4 VMs and the optimal number of backbone namespaces, we achieve our goal to construct 10,000 node virtual networks with several minutes across all the 3 topologies. We also compared our SplitNN with APNet, a state-of-the-art satellite network emulator from last year APNet. For the same topologies, our SplitNN can be 20 times faster, cutting the construction time by up to about 99%. These experiments prove our SplitNN's great performance in large-scale network emulation. And that's all. Thank you for listening. And here we list some public resources, including a public platform we built for large-scale network emulation. And we will welcome users and collaborators from public. And now we are happy to take any questions. Thank you.
Okay, thanks.
Hello.
Hi.
Yeah, here is one question. I see it's great work, and it reduces construction of the mega scale emulation system greatly.
Yeah.
But construction just is one thing. Another thing is processing. Is your work have great benefits when processing the traffic inside your single machine system?
Yeah. That's a great question. And basically, the question you mentioned is basically, I think, is orthogonal to our work. So indeed, we only address the virtual network construction here. And for the processing in, like traffic processing in the network emulation, I think there are many other optimization work like time dilation or some other time dilation works, and we are still exploring.
Okay, except for the traffic processing,
Yeah.
Is there any benefits about memory resource reduction?
Yeah. So we are not reducing if you use the SplitNN we showing here, we do not reduce actually we just build the virtual network frameworks for the application that you want to run in the virtual network. And we found that in practice, the memory consumption in the network emulation is usually dominated by the application in each container or the virtual machines. And in this work, we did not address this. But I think there are many chances, like we can somehow break the isolation, somehow compromise the security between these containers and share the code segment or data segment of these virtual nodes. And that may reduce the memory very sharply, since there are many routing tables in each vNode, right? If we can combine them or reduce them using a more dedicated data structure, I think that will help a lot.
Oh, thank you very much.
Thank you.
Okay, thank you for your presentation.
Yeah, thank you.
Okay, we have 3 very great presentation. Okay, let's welcome the chair of the second session.